Last time we looked at this graph and saw how it satisfied the wave equation. D squared y over dx squared is equal to minus y. The solution that we arrived at included two arbitrary constants, a and b. By varying these constants, we can make this wave take the shape of any possible sinusoidal wave. Essentially, the differential equation contains all the different varieties of the waves. The question that now comes to mind is, how do we get these differential equations? And that's what we're going to answer this time. To get the differential equation for a family of curves, we need to get rid of the constants in the equation. For example, let's say you have the equation for a circle. X squared plus y squared is equal to r squared. This equation looks something like this. These are your axes, y-axis, x-axis, and this is your circle. This circle has a constant radius, r. That is what defines a circle. We need to get rid of this r from this equation by differentiating this equation. So we proceed by differentiating it once to get 2x plus 2y dy over dx is equal to 0. Note that this eliminates the constant r, and now what we have is a differential equation. We can simplify this to write x plus y dy over dx is equal to 0. And this is our differential equation for a circle that is centered at the origin and has a radius r. Okay, let's see one more example. Let's say you have the equation for a straight line. Y is equal to mx plus c. A straight line with a slope of m and a y-intercept of c. So let's say this is your straight line, y equals to mx plus c. This is your y-axis, this is your x-axis as usual, this is your origin, and this is your straight line. M is the slope and c is here, that is the y-intercept. As usual, we will get rid of these arbitrary constants, m and c, to get a differential equation. We differentiate it once to get dy over dx is equal to m. To get rid of m also, we need to differentiate it once more, so that we have d squared y over dx squared is equal to 0. Now we have gotten rid of both of these constants. And this is the differential equation for a straight line. This was for a circle, and this is for a straight line. Now, one thing and a very important thing to note is that this equation of a circle had one arbitrary constant, r. And the differential equation that we have for the circle is of the first order. The equation of a straight line, on the other hand, had two arbitrary constants. And the differential equation for the straight line is of the second order. And this is not just a coincidence, this is in fact what we will see every time. The number of arbitrary constants is always equal to the order of the differential equation. And this fact will make sense when we learn about how to solve differential equations. Every time we integrate a differential equation, to reduce its order, we have to introduce one arbitrary constant. And so for a first order differential equation, you have to integrate it once and you get one arbitrary constant. For a second order differential equation, you do it twice and you get two arbitrary constants, and it's just like that. We will solve differential equations pretty soon. For now, let us find the differential equation for ellipses. The equation for an ellipse is x squared over a squared plus y squared over b squared is equal to 1. This equation has two arbitrary constants, namely a and b, the semi-major and semi-minor axes of an ellipse. So this equation contains all of these ellipses. This is your y-axis, this is your x-axis. So all of these ellipses, and if I can draw it properly, all of these ellipses are the members of this family of curves, represented by this equation. So in order to find the differential equation, we do the usual, we differentiate it once first, so that we have 2x over a squared plus 2y over b squared dy over dx is equal to 0. Now we would like to rearrange this a bit so that we have an easier second derivative. So x over a squared is equal to minus y over b squared dy over dx. Now we can rearrange this a little more so that we have a constants on one side, and we can just get this 0 on the left hand side, and on the right hand side we have y over x dy over dx. We would differentiate it again and get rid of both the arbitrary constants and now get a second order differential equation. So this implies 0 is equal to, now we would have to use the differentiation rules. So we differentiate this while keeping this constant and then this while keeping this constant, the product rule. So y over x d squared y over dx squared, this plus now this constant and the differentiation of this, so dy over dx multiplied by, and this here we have to use the quotient rule. So we have x squared and x times the derivative of y dy over dx minus y times the derivative of x, so that is just 1. So we can further rearrange this and maybe multiply this by x squared so that we get xy, this term would be xy d squared y over dx squared plus dy over dx multiplied by x dy over dx minus y, and this whole thing is equal to 0. And this now is the differential equation for all the ellipses. Note that this is second order differential equation because we had two arbitrary constants a and b. It is a good idea now to practice what we just learned. Try obtaining the following differential equations. In the first question, you have the equation for hyperbolas with two arbitrary constants a and b. Similar to what we did in the video, eliminate these two constants and get a second order differential equation. In the second question, we have the equation for the family of parabolas represented by y squared equals to 4ax with only one arbitrary constant, that is a. Eliminate this and get a first order differential equation. The last one is a bit tricky. You need to first obtain the equation for the circles that are touching the x-axis and passing through the origin at the same time. Try doing this and then obtain a differential equation which will obviously be different from what we obtained for circles. Those circles were centered at the origin and had a constant radius of r. For this, you need to first obtain the equation for the circles and then find the differential equation. As a hint, you can look at how the circles that we are talking about look like. Once again, I have used Desmos to plot these circles, and you can see how these circles touch the x-axis at the origin. One thing to note is that the centers of these circles lies on the y-axis, so you can take this as a hint. Obviously, I'm not going to tell you what the actual equation is, but at least this is a hint for you.